So our next speaker is Marie Sar, and she will talk about cosmic voids and CMB.
Thank you. So, hi, I'm Mar. Thank you for having me today. It's a challenge to talk after John Fico, but I hope it's also interesting for all of you. I want to introduce you this project. It's about the forecast for the Roman telescope, but I will include also all the lessons that I've learned all the way. This is a project that I've been doing with my supervisors, Andres Kovacs and Carlos Hernández Monteagudo, but everything started with Alice Pisane at the Flatiron Institute. Okay, sorry. Okay, so I will introduce a little bit what, why, and how I'm going to do this project. Basically, what I'm going to measure, we already know about voids and we already know about CMB lensing, but I will just remind, like, voids are under dense regions in the large scale structure. They are biased tracers because it depends on the galaxies that we use for detecting them, and they allow us to map 3D properties of the cosmic web. And for the CMB lensing convergence, we cannot use the deflection angle by itself because we don't have a lens map as a reference, but we can use the derivatives of this deflection angle. And one of those components in this magnification matrix is the convergence. If you have a circular bundle of photons coming towards you, you can have a smaller circular bundle. The convergence will be positive or divergence. And then you also have shear when the shape also changes or rotation. So it remaps the CMB temperature and polarization. It's a 2D observable and it's an unbiased tracer. So why I was interested in this? First, because I wanted to know Roman's capabilities. Second, because there were kind of some tensions in the literature. Here I see some of the works that are in the literature about voids for CMB lensing. In different colors you have different surveys. All of them are below redshift 1. And in squares you have some of the works that show some tensions. These tensions seems that are due to methodological choices like subpopulations of voids or maybe some mock catalog that it's not mapping well enough what the survey sees. And I wanted to check what Roman will look like in this context and what I can add to all this work. So connecting a little bit what was discussed yesterday, how we can move forward. We need more data, we need better data, or maybe we need better models, because all of these works are simply detecting the signal, which is nice, but none of them are constraining cosmology. So I will take advantage of what are the simulations that we have now and try to understand better our models, let's say. So yes, the challenge that we need to overcome is that we don't have a robust analytical model, so we need to rely on simulations and template fitting. So we measure the signal in simulations, we measure the signal on data, and we compare how well they match. But if we want to constrain cosmology, we need a very large set of simulations spanning with many cosmologies, and more difficult that has CMB lensing companions. So only a handful of simulations have also CMB maps, like Agora, the Munich, Haltom, but most of them only have lambda CDM case, just a realization of that case. And beyond that, all the collaborations have really precise mock catalogs for the surveys, but they don't have CMB maps. So we need to go to simulations and create approximate mock catalogs for these really precise survey. So we need to check also how these approximate mock catalogs that we are doing are affecting the lensing signal. And yeah, like the observations I mentioned. So to move beyond this signal detection, we want to study how this void density profile respond to cosmology and how to respond to methodological choices. In this work, I just check the methodological choices. So the reference catalog that I am using is the Sai et al. 2021, and I'm using the Agora simulation of Yukio Mori. Basically, for doing my mock catalogs, I'm doing an analog matching method, which means that I'm taking the closest neighbor from the simulation Agora that resembles to the reference catalog. So imagine that I have 10 halos that have a given mass. I try to take those same halos in my Agora simulation. The parameters can be as complex as you want, not only the mass, but also the environment or other type of biases. So basically what I first did was subsample a little bit the Agora files, first to make it also more feasible to play with, but also to introduce some little bias in these files. So for example, I select sample of tracers regarding the mass, so the most massive tracers, then the most massive but only ELGs, then randomly subsampled all type of galaxies and also ELGs. So I've introduced 4 types of biases in these files, and then I apply my analog matching method. Then I find the voids in 3D and 2D. So 3D I use Revolver, 2D I use the Sanchez et al. Algorithm, which just projects density maps and then founds under densities on them. And finally, I measure the signal. I preprocess the CMB map by applying some smoothing, which removes some of the instrumental noise. Then I stack the signal, cutting patches in voice position, rescaling, and measuring the profile. And then for the uncertainties, I repeat the same procedure, but I replace the map with random fluctuations, with the same power spectra, but randomly distributed. So first of all, how different mock catalogs affect void statistics. Here I will divide in 3 columns. First, the first row will be the number of voids in 2D and 3D, then the size, and then the minimum density. So just little by little, what you see as a first look is every column in 2D and 3D is one of the methods. Like the first one is only taking into account to match the number of objects without regarding anything else. Then number of objects and mass. Then mass and also environment. And mass and the type of galaxy. So as you can see in the 2D voids, we don't see a lot of change. By the way, the different colors in each of the panels is this slight different bias that I introduce in every method. So I check how every method responds also to different types of biases. In 2D voids, we don't see a lot of difference, but in 3D voids, yes. For example, if we have a sample that matches the number density but is made up of most massive objects, then you have fewer voids and bigger. Then if you have a randomly selected sample, you will have fragmented these voids. This is something that you can see in the void size function, especially in the 3D case, and also there are some apparent difference in the minimum density. For the 2-point statistics, it's clear that for the first case, you clearly see the bias of the clustering of the tracers. For the second and the third method, you basically dim the differences of these initial files, so you get up with the same effective bias. And with environment, it's a little bit complex, and I can answer questions afterwards. For the 2-point statistics, again, you see some differences according to the methods and the different bias of the tracers. So Boyd and Galaxy statistics are significantly affected by the method used. These analog matching methods that incorporate halo mass and also the type of galaxy are the ones that give better results. And 3D Boyd statistics generally exhibit more changes in this across these different mock catalogs. So now, how different mock catalogs affect the lensing? If we have seen that we can clearly see differences in these statistics, how is the lensing? Well, this is just to see how the lensing profile would look like. And what we can see is that even for 2D and 3D voids, we cannot see those differences. So the lensing profile is more or less similar between all of them. Here I'm not introducing any instrumental noise, so everything will be within the instrumental noise. We can also see if this is depending on the void profile, because maybe here we are averaging something, and maybe there are some differences if you divide by void type. Here what I show is I compress all this information in 3 points, like the initial part of the lensing profile, the maximum point in the wall, and also the difference of above the 1 void radius and minus 1 void radius. So in the first panel, you have the first point, the maximum point in the wall, and these differences. And between all the catalogs and all the different biases that I've introduced, all of them looks very consistent. So it seems that yes, that the lensing profile is not really affected by the mock catalog that you are using, even if you are messing up a lot. For the signal to noise, very quick. Even if they present the same lensing profile, they have different void statistics, so they have different noises also, and exhibit a little bit of differences. Yes, like the void across CMB lensing remains stable across different mock catalogs, which is really great when trying to deal with tensions and find a reason for a tension in the data. It seems that it's insensitive to bias, as I said, and unlikely to be the main cause of tensions with real data. Finally, I did the forecast, which was the first step that I wanted, but I just get lost in the way. And I did the forecast for 3D and 2D voids with 2 setups for the 2D voids, and checking different smoothings of the map and different instrumental noises. Basically, with 2D voids, you can have a higher signal to noise, but still are very interested in 3D voids and so on. Yes, improved sensitivity. Current plant data is noise limited, but upcoming experiments, Ames Observatory, CMB, stage 4, maybe not anymore, but will greatly enhance signal to noise ratio. And since I'm in the time, I will leave the highlights here. Thank you.
Questions? Well, I will ask one. So you talked about different cosmologies. So what is the expected effect of different cosmologies? For example, I saw you internalize anomaly simulation. So what is the effect, for example, neutrinos?
That I'm not checking in this work, I'm just checking how different mock catalogs are affecting, but there are some effort going on by Mina and also Barbara checking how different omega matter and so on impacts the 2D void profile, but I'm not checking it, sorry.
Questions? All right, I guess we can move on.